Okay, so hi everybody. Uh, just as a change of pace, we're going to go through a couple of example problems to illustrate how to use the relationships between frequency, wavelength, and electric and magnetic field strengths for electromagnetic waves. So for this first problem, we are told a particular radio station utilizes frequencies between commercial AM and FM. To avoid interference with these common bands, which is phrased badly because it's basically saying that this frequency, 11.62 megahertz, is between AM and FM radio frequencies. So the question, which is straightforward enough, what is the wavelength in meters of an 11.62 megahertz wavelength chip? Well, this is a relatively straightforward thing to approach and we'll do this with our same basic procedure. So what are we looking for? We're looking for lambda, the wavelength. What do we know? Well, we know the frequency. We know the frequency is 11.62 megahertz. And just to apologize again for my ability to draw with this system. So this is what we want. This is what we know. What relates those two? Well, it's this relationship that the speed of light is always the frequency times the wavelength. That's a relationship that connects those two quantities. Now, do we have everything we need? We're looking for lambda. We're given F, and but we have this final thing, C. Well, fortunately, we know what C is. C is the speed of light, and that is one of those fundamental constants of nature. It's 3 times 10 to the 8 meters per second. So we actually know everything in this relationship. So all we have to do is solve for lambda. Lambda is going to be C over F. And notice this relationship makes sense. If F is big, lambda is small, and vice versa. So now all we have to do is actually evaluate this, which means sticking in the relevant numbers, which we can do here, but it's easy enough to do in this particular environment. So what we can say is it's going to be 3 times 10 to the 8 over parenthesis 11.62, but then we have to multiply that by 10 to the 6 because it's megahertz. So we get, that should be the expression, and we could submit that. And what we get is the correct answer. The wavelength is 25.82 meters. Notice this makes sense. C has units of meters per second. Frequency is 1 over seconds. That's what hertz is. So the units are meters. 25.82. So the wavelength of this sort of radiation is 25 meters, which is quite large when you think of that. And that's one of the reasons to do these sorts of problems. Okay, so that one's straightforward. Let's look at problem 2. This is another example of this sort of type problem. Consider an electromagnetic wave with a maximum magnetic field strength of 6.5 times 10 to the minus 4 Tesla. And we're asked, what is the maximum electric field of this wave in kilovolts per meter? Again, that is a unit of electric field. It also could be newtons per coulomb, but remember, volts per meter is also a perfectly valid unit. So we can approach this in a very similar way. First, we can get rid of all of this stuff over here. And we can work on our next problem. Erase, erase, erase. So in this case, what are we looking for? We're looking for the electric field's strength, the maximum, which is the amplitude, which I will call E naught. What do we know? So this is what we're looking for. What do we know? Well, we know the maximum magnetic field, which is given as B, but I'm going to write it as B naught just to be clear on this. And that, we are told, is equal to 6.5 times 10 to the minus 4 Tesla. Okay, what relates what we want to what we know? Well, this is that same relationship that we talked about today, which is that the electric field magnitude is the speed of light times the magnetic field magnitude. Now again, does this have everything we need? Well, we're looking for the electric field magnitude. We know B naught. And we also know what C is, because C is, again, this fundamental constant. It's just going to be 3 times 10 to the 8 meters per second. So again, this is a straightforward relationship, and we can just plug in the numbers. So E, and this is even in the correct form, so we can just put in the correct values. E naught should be 3e to the 8 times 6.5 e to the minus 4. Now, if I enter this, this will tell me that I got the wrong answer, because this is what units is this going to be? Well, we know it's going to be Tesla meters per second. That's not kilovolts per meter, that's volts per meter. So if we want to get this in kilovolts per meter, we have to divide by 1,000, because there's 1,000 kilovolts in every volt. So we do that. What do we get? Now we get the correct answer. Turns out it's 195. Unlike, say, frequency and distance, where we have a sense of what things are, is this a plausible number? It's very hard to say, because we don't have much intuition for this. But it worked out. It does show that there's a relationship between the two. But what's more useful is to get a sense of this, and that's what problem 3 is for. And again, we will do some erasing to clean up our board or screen or what have you, which is fine. But we're going to ask for a problem that's a little more practical this time. And again, we're focusing on radio signals just because they're the easiest thing to deal with for these sorts of problems. So a 4.5 meter diameter university communication satellite dish receives TV signals from that have a maximum electric field strength for one channel of 7.5 microvolts per meter. Okay. We are now asked, what is the intensity of this wave in watts per meter squared? So this is, again, an electric field strength. It's like, what does that even mean? It's small compared to the one we calculated, but what does that correspond to in terms of intensity? Well, let's look into that. Let's try and calculate that from this. What are we looking for? We are looking for, and I will just give myself a little more space because this one is going to be a little more complicated. So, first of all, what are we looking for? We're looking for the intensity. And I will say this is an annoying thing. the intensity of this signal is I, which is also the symbol for current. We're not talking about current, we're talking about intensity. Okay, what do we know? Well, we know the size of the dish that we're receiving this with is 4.5 meters. And we also know the electric field magnitude, which I'll just write as E naught again to try and be consistent with my own notation, which is 7.5 microvolts per meter. Okay. Now, what relates what we know to what we don't, to what we know to what we want? Well, we know of one relationship that tells us what the intensity is in terms of the electric field. That's I naught equals E naught times B naught over mu naught and 2. Okay, let's look up now. Is this okay? Well, we want I naught. This expression's already for I naught. That's good. We know what E naught is. It's written right here. We know what mu naught is. Mu naught is, again, this fundamental constant. It is, as we've said before, it's basically 4 pi times 10 to the minus 7 with some units attached to this. And I'm not going to write out all of them because they're kind of awkward. So you don't give me too much of a hard time for that. I'm just going to erase that again. We know what mu naught is. What about B naught? We don't know that. We're not told it, but we do know what it is because we have another relationship. E naught is C B naught, which means B naught is E naught over C. We know what E naught is. It's 7.5 microvolts per meter. And we know what C is. That's another one of those fundamental constants. So we can rewrite this expression for the intensity in the following form. We just put in E naught over C for B naught, and we'll have E naught squared on the top because we have E naught times E naught over 2 mu naught C. Now we have one thing we know. Yep, that's good. And we have fundamental constants. Notice D doesn't enter in here. The size of the dish doesn't matter for the intensity. This is just something about the wave. So at this point, we can stick in some numbers. So let's do that. So we're going to say the numerator is 7.5, 10 to the minus 6, because it's microvolts per meter squared. We're going to square that. And then we're going to divide that by 2 times 4 pi times to the minus 7. Apologize if I said 10 to the 7 to start with. This is in fact right. times 3e times 10 to the 8. And let's submit that, see what we get. That was the correct answer. The intensity is 7.5 times 10 to the minus 14 watts per meter squared. So we're talking very low amounts of stuff, power going into this thing. So the end result of that calculation, just to say it, is, and so let's see, how do we want to do this? You now say I naught equals, and I'll round this off a bit, 7.5 times 10 to the minus 14. We're going to get a little close to space, but that's okay. Watts per meter squared. So again, this is how much power is delivered per square meter. Okay, let's consider the next part of this problem, because I think that this will bring down where things get a little more practical. Part B. What is the power received by the antenna in watts? Now we're going to talk about watts, so we can compare that to like light bulbs and other things. What are we talking about here? So let's erase some of this. Let's get rid of all this stuff. We already know what the thing is. So we got all that. Okay, I might as well erase that too. Okay. So now in this case, what do we want? We want the power, which I'll designate with P. What do we know? Well, we know the intensity, we know the electric field, and we know the size of the dish. Now, here's the thing. Again, intensity is how much power gets through a given area. What relates what we know to what we want is the power is always going to be the intensity times some area, which I'll designate with A. Now, that area can be the area of a sphere surrounding a source. It can be anything. It depends on the problem. In this case, what is A? Do we know that? Again, look at the problem. We want P. We know I naught. The question is, do we know A? And in fact, we do. We need the area of this radio antenna. Well, it's got a diameter of 4.5 meters. It says right there. So we know the diameter, and there's a relationship between diameter and area. We've talked about that before. It's pi over 4 times the diameter, d squared. And we know what d is. It's 4.5 meters. So the total power received by this radio antenna is going to be, I should write this out properly, I naught times pi over 4 d squared. Okay, we got everything we need. We know I naught, it's written right here. We know d, it's written right here. Everything else is a constant. We should be able to make this work. So let's try it. So 7.5 e to the minus 14 times 3.14 over 4 times 4.5 squared. Let's see what that is. Got the right grade, so it's all good. So what do we find? The power is 1.2, 1.1 times 10 to the minus 12 watts. This is a tiny, tiny signal. The amount of energy that we are delivering to this radio antenna is small, and that's common in communications. You have to have fairly sensitive instruments to pick up signals like this. You know, and this just to give you a sense of a pretty small electric field corresponds to a pretty small power delivered to even a fairly big radio dish. Now, part C, for just amusement's case, is you can say if this signal is supposedly coming from an orbiting satellite that broadcasts uniformly over an area of some huge number, 1.5 times 10 to the 13 meters squared, which is basically a large fraction of North America. How much power does it radiate in watts? So this is a question of how much energy is the satellite emitting. Again, it's the same expression. Power is this times area. But in this case, area isn't pi d squared. It's just this number. So we can just try this out and see what the value is. So it's 7 times 10 to the minus 14 times 1.5 times 10 to the 13. Evaluate that. You've got something putting out about a watt worth of power, which you think a spacecraft, sure. Usually they can put out quite a bit more than this, but this is just giving you a sense of how kind of sensible numbers of amounts of power, maybe a watt from a spacecraft and something we can read, correspond in terms of electric fields. So this is just an example. You will have many other, you have a number of problems on your own assignments to work through that are similar to this. And hopefully this will give you a sense of how to approach those. Thank you very much.